So this video is going to go over the background information to the spectrum lab that we did, more specifically about the emission spectra. So find this diagram in your note packet and write on the top emission spectra notes so that you know that these are going to be the notes that you need to refer to for this. So over here on the left, we're going to draw a little diagram. So I'm going to shift it where it's a little open here, an open space. And we're going to draw some energy levels. So I'm going to draw a line here and call this energy level 1. Then I'm going to draw one up here and call this energy level 2. And then this next line, make it a little closer than the distance between energy 1 and 2. So again, the further away we get from the nucleus, so if this is the nucleus down here, the closer the energy levels get. And then draw one more and call it energy level 4. Again, being even closer than 2 and 3 are. So in the emission spectra, we were putting the glass tube into a contraption that gave it electricity. So write energy in. So this is again going to mimic what we did in the flame test. But what I want you to write is electricity is really what we're adding to the sample. It's still going to do something to the electrons, but for our intents and purposes, we are putting electricity into it. So it's different than the flame test. So draw yourself an arrow. I'm going to do 2 different colors. So I'm going to do black and red in the first energy state. So let's say this is the 1s and then this is the 2s, 2p, so on and so forth. And again, that's not all that important at this point in terms of our discussion. Okay. So as we put energy in, as we discussed with the flame test, the electron is going to move to a higher energy state called the excited state. So again, where it starts off is the ground state and somewhere above it is called the excited state. So let's say I have enough energy to move the electron up to the 4th energy state. Okay, and again, I have to put a quanta of energy in to get that to go up there. The quanta of energy you put in has to equal the quanta of energy you put out. So let's say this electron went down to energy level 3, okay? Well, when it does that, a photon of light comes out, okay? And when the photon of light comes out, that's going to not be all of the energy that was put in, just a part of it. So the electron, once it goes to an excited state, can come down many different ways. So let's say it goes down to energy level 3, and then let's say it goes down to energy level 2, and then it goes down to energy level 1. Well, each time that happens, it releases a photon. Okay. And so that is why, or that is a way to think about the fact that why do we see the distinct lines that we do in emission spectra? Well, it has to do with, again, what kind of transitions is it going through? So this is what we call multiple transitions. So in the first discussion, when we were talking about this with the flame test, we were saying things like, okay, one electron is moving up to one energy state and coming back down. A lot of scientists focus on hydrogen because it has one electron and it's easy to track one electrons. But as we know, when we were putting in lithium into the flame, or we're putting potassium chloride into the flame, we have multiple electrons that could move. So the electrons could, you have multiple electrons, but also you have multiple transitions, meaning the electron could go up to a higher energy state and come down one at a time, or could come down all at once. So again, if I take the red electron here and move it up to energy level 4, I could also have it come down and release a photon, again, because it went from energy level 4 to 1. So I did it all in one swoop. So because you have different transitions, you're going to have different photons coming out because these distances between the energy levels are not the same. So therefore, the light that's coming out is going to be different. Okay, so that's why we call them multiple transitions. 1, because you have multiple electrons, but 2, you could have them coming down at different ways. Okay, I could have energy level 2 or energy level 4 go down to 2 and then to 1. Okay, I could have this one go down to 3 and then to 1. It could do all sorts of different things. So again, that is what we're trying to show with this emission spectrum. So now direct your attention to this Bohr model again. and to kind of help you out with what these little squigglies are. So essentially, this is an electron that's relaxing back down to its ground state. So again, it was promoted up by a quanta of energy, but now it's coming down. And what we care about is when it's coming down. So this is energy level 4, and it's going down to energy level 1. This is energy level 3, and that's going down to 1. And this is energy level 2, okay? So not by telling you anything else about this, energy level 4 to 1 is a longer distance. Okay, since it's a longer distance, you're going to have a different amount of energy compared to the distance of 2 to 1. So therefore, you have a difference of what is it showing up in the emission spectrum. Okay, so again, the only thing I don't like about this spectra is it's kind of backwards. Okay, so if you want to look back on your electromagnetic spectrum, we have been focusing a lot on the extremes. And the one thing we're going to focus on with the visible range is red versus violet. Well, when you look at violet and you see its wavelength, okay, it has a short wavelength of very high frequency. If we know energy is equal to Planck's constant times frequency, the higher the frequency, the more energy it's going to have. So violet is a higher energy state than the red. Red is a lower energy state when we're talking about the visible range. So the more higher the frequency, the higher the energy is going to be, okay? So I can really take this and draw it the particular way, just kind of backwards. So if you have colored pencils, you could take them out or some kind of thing, but we're going to write red on this side and we're going to write violet on this side. So that's the only problem I don't like about this diagram. I think it's a beautiful diagram because it shows exactly what we're talking about, but it's kind of backwards to how we have the other electromagnetic spectrum where we have red on the left and violet on the right. It just depends upon, again, the author of who's writing what. Since N2 to N1 is going to be less energy, we could say that that is the red line that you're creating here in this emission spectrum, because it is a smaller energy than, say, from energy level 4 to energy level 1. So I could color this a violet color, okay? And maybe, again, you would actually have to do the math. Maybe this is the blue line that you see here, okay? So red is on the right, less energy. Violet on the left, more energy. Because again, we're going from 4 to 1 versus 2 to 1, okay? So this emission spectrum is going to be, those distinct lines have to do with each transition that is taking place. So it could be one electron going from 4 to 1, 3 to 1, 2 to 1, or it could be multiple electrons. The stronger the band is that you see, the more likely that transition happens, okay? And if you watch that one video that I gave you, it does show you how that emission spectra is created. It's a pretty nice video. So again, this emission spectra is a fingerprint for that element. So if it is hydrogen, it is always going to have the same emission spectrum. If it is oxygen, it's always going to have the same emission spectrum. So that is how scientists could see far, far away on those stars that we have hydrogen mostly in our universe, and so on and so forth. But again, this is what scientists use to identify things. It's used to figure out if there is different energy levels, which we now know is true, because if these were all equally spaced, you would see the same line showing up. And we now understand more electrons can be involved, and so you could have more and more transitions. Okay, so that's what the emission spectra tells you about the atom.